Okay. Electron affinity. Remember, when an electron gets pulled into an atom, it gives off some energy. It actually gives off a little bit of heat energy. It makes the atom vibrate a little bit. Trends in electron affinity. Let's write down some of our trends here. Oh, I'm getting rid of nuclear charge, folks. What am I putting instead of nuclear charge? Yeah, number of protons. Number of protons, just because it keeps things a little simpler. And I am a fan of that little add-on with the same number of orbits. I do really like that statement. Our ionization energy and our electron affinity arguments are exactly the same. Low electron affinity doesn't want to pull on a neighbor's electrons. Low ionization energy doesn't even want to pull on its own electron. Something else could take that away. So they do the same thing. Low ionization energy, low electron affinity. High ionization energy takes a lot of energy to take an electron away from fluorine because it's got a strong pull on it. And if it pulls on a neighbor's electron, it's going to pull in hard. They do exactly the same thing. Low, low, right? Low, and high, high. But a good metal, a low ionization energy, makes it a good metal. But a good nonmetal, a high electron affinity, makes it a good nonmetal. So what makes them good are opposite. And that's why we have opposite parts of the periodic table. So again, it's all about the pull on the electrons. The nonmetals have a strong pull. So across the period, for nonmetals, reactivity increases. More reactive. And down a group, the reactivity decreases. So again, the most reactive nonmetal, fluorine. So you can now complete that electron affinity nonmetallic character piece, but there's one more thing I want to talk about before I let you do some work. And that is something we call electronegativity. And again, our explanations become the same, but this is kind of a new, well, ionization energy and electron affinity have been a new concept. But this is a concept that becomes very important when we start to talk about bonding. And hopefully you have your periodic tables nearby, because we're going to be looking for some numbers on the periodic table. You're going to be using these numbers in the future, and I just want to introduce you to where to find that number, because as you know, that periodic table is full of all kinds of information. I'm slowly pointing out to you where the good stuff is, right? At this point, we've looked at things like the atomic number and the mass number, and now I want to point out to you, like I said, the electron affinity. Oh, sorry, the electronegativity. All right. Electron affinity is a measure of energy. We just did that. How much energy is given off when an electron crashes. Ionization is a measure of energy. How much energy is needed to take an electron away. Those are all physical properties that can be measured in the laboratory. Electronegativity is not actually a real physical property. It's a number that has been calculated by chemists that represents how good an atom is at sharing. Oh, isn't that nice? It's like a sharing number. So good, so nice. We always teach you in grade 9 and 10, either there's ionic bonding, right, where there's a transfer of an electron, some big bully of an atom takes an electron away from another one, and then there's covalent bonding, where they share, right? As if it's kind of, and everybody thinks, oh, those covalent guys, they're so nice. It has nothing to do with sharing. In reality, it's more vicious than that. It's really more of a tug of war. When you have a bond formed between two atoms like chlorine and hydrogen, right? Chlorine's got its extra electrons out here, and it's going to have one of its electrons in this bond, and hydrogen's going to supply its electron to the bond. So these represent their electrons. And they supposedly share so they can get a full outer shell. Well, that's not really the case. If we talk in terms of ionization and electron affinity, both of these things have fairly high ionization energies. They don't want to give their electrons away. They're not like cesium and francium and rubidium, which means when another atom comes along and says, hey, I want your electron, they're both going to say, no, I don't think so. I want my electron. High electron affinity. They also have, high ionization energy. They also have high electron affinities, which means when chlorine comes along to hydrogen and sees its electron, it says, I want yours. I want yours and I want mine. I don't want to share it all. I'm going to take your electron and I'm going to keep my electron. And hydrogen, because it's also high up there, does the same thing. Oh yeah? Well, I want your electron and I want mine. So in the end, the only way that they can be satisfied with getting electrons, if no one's going to give it up and they're both pulling on each other, the only way is to stand beside each other. That's what a covalent bond is. Now it turns out when the atoms are different, one atom is a little stronger at pulling than the other. And that makes the tug of war, all right? Take a look at your periodic tables, and I don't have a copy of it right here, but in the legend you will find that there is a location that gives us what is called the electronegativity, and it is near the top. It is to the right of the box, and it is above the name. Do you see the electronegativities? All right. So for hydrogen, what's the electronegativity? For hydrogen, what's its electronegativity? Yep. I think 2.2. I think there's a decimal in there. I hope there is. 2.2. 22. Wow, that would be like a muscle-bound hydrogen. That'd be like a super hydrogen. How about the electronegativity for chlorine? What do we got? Yep. 3.16. 3.16. What that means is that chlorine is a little stronger when it comes to hydrogen and pulling electrons. All right? And what that does is, in the end, when they go to share, they really can't share because they're pulling, right? It's a tug of war, and chlorine's a little stronger. So what that does is it pulls the electrons a little closer to chlorine. So the electrons are actually not equally shared. They're unequally shared. So electronegativity is a measure of how an electron pulls, how an atom pulls on electrons while they're in a bond. Okay? What we talked about previously, ionization energy and electron affinity, it's just pulling on electrons, not while they're shared in a bond. So it's a bond kind of pulling number. We want to talk about the trends in this number, and the trends follow the exact same thing. As you move down the periodic table, the electronegativity goes down because it has more orbits and the electrostatic force is weaker and it doesn't pull hard on that other electron for the same reasons. As you move across, I'm changing nuclear charge. Hopefully you've already changed it yourself. If you haven't, it's not a big deal. I'm putting numbers of protons. And that's a little P plus there if you're trying to figure out what I'm writing. As you move across the table, same number of orbits, number of protons increases. It pulls on those electrons that it's bonding, and it increases the electronegativity. And when you're done writing, if you take a look at your periodic table, you can notice that. You know, if you go from, say, boron across to fluorine, you'll notice the that number just steadily goes up. So that's the end of the trends that we need to know, all right? What I want to do just now before I let you start working, plenty of time here. You're going to got a great deal. You're going to be able to work on the rest of that worksheet, all right? And I'm going to give you the review questions that you then can work on in preparation for the test. I've got one more thing I want to do, and I'm going to just use the Smart Notebook feature here, and I do want you to write this down. I want to simply summarize all the stuff that we saw. All right, I just want to put a summary of all these increase in this and decrease in that and all that type of stuff. And so what I want to do with this is I want to start by just drawing a blank periodic table. And you'd be surprised it's easier than you think, right? If you take a look at the general shape of the periodic table, it's got a little step there and a little bump, and then it's got a couple of other bumps there. So simply, right, draw a box that has like a bump, and then a line across here, and then another bump here, and then what do we got? One more bump at the top, and that'll do. And actually, I made it too far to the left. I'm going to clear the screen, and I'm going to do a new one. You can draw it up, but I'm going to do some writing here on the left, right? So I'm going to do some writing here on the side. So I'm going to start a new one. We'll put it more in the middle here. What am I doing here? Oh, pen. Oh, that's the worst table ever. What the heck is that? That's like a high chair. My goodness gracious. Terrible. All right, good. Beautiful. Excellent. Okay, so let's just do some summary here. As we move down the periodic table, all right? So as we move down the periodic table, some of the stuff we talked about in terms of atomic radius. Does that make sense, atomic radius, the AR? You might have to write that down at the bottom. I don't know. What does the atomic radius do as we move down the periodic table? What happens to the size of the atom? Yep, it gets larger. And I'm going to just put an arrow up because I don't have enough room for increases. But I think we get the idea, right? The atomic radius increases as we move down the periodic table. We talked about ionic radius, and we compared ions and all that type of stuff, but we didn't really compare trends of ions. If you're talking about stable ions, as you move down, they get bigger as well because they get more orbits as well. So we're not really worried about that type of thing. The next thing we talked about was the ionization energy, the amount of energy needed to pull that electron away. What happens to the ionization energy when you move down the table? Yeah, Janessa? The ionization increases. It's going to become harder to take those electrons away as we move down the periodic table. It decreases because they're getting larger and they're really easy to pluck away. It decreases. Excellent. All right. Now, down here on the bottom, just before I talk about the next one, which is metallic character, for a good metal, what kind of ionization energy do I want? If it's a good metal, yep, low. Low IE results in a good metallic character. They're opposite, right? Low ionization energy, don't care about my electron, fabulous metal. So as we move down, the ionization energy decreases. So what happens to the metallic character? It increases. It's the opposite. It does the opposite. Right? Okay? And we can do the same for electron affinity. Electron affinity. What happens to that pull on that electron as it comes in as you move down the periodic table? Atoms are getting bigger. It's still a pull, It's just a pull on the neighbor's electrons. Makes a difference. Same trend. What happens to that pull? It decreases. Ionization energy and electron affinity is the same. Not only does cesium not care about its own electron, but it doesn't care about the neighbor's electron. No pull whatsoever. Okay? This is kind of a silly thing to say, but if the metallic character increases as you move to the bottom where you've got the rock star of metals down here in the corner, what's going to happen to the non-metallic character? The non-metallic character, yeah, it's going to decrease. You cannot have a good metal and a good non-metal in the same spot. It just makes no sense. The reason we can say that is for a good non-met, because just to put AL on the end would be way too much work. When you make study notes, you want to make things tiny. For a good non-metal, what's true about the electron affinity? It's high. High electron affinity results in a good non-metallic character. It's the same, where the other one is opposite. Okay? So let's work our way across then. Across the table. If you don't have room above, you could put all this information underneath. It's still working its way across. And I'm simply going to go through all of these same, things that I just talked about here. Atomic radius. What happens to the atomic radius as we move right? I'm going to pause. Emily's arm must be tired. I got multiple Emilys here. Hands up, Chris. Across the row in the middle here. Let's ask Connor, what do you think? What's going to happen? What happens to the pull as we move to the right? It increases because there's more protons. If there's a greater pull, what's that going to do to that outer orbit? Make it smaller. So as we move right across the periodic table, the atomic radius actually decreases. All right? Let's talk about non-metallic character before we go back and talk about this. So I'll just move over here. Let's go with electron affinity. EA. What happens to the electron affinity as we move right? Yep, Jory? Increases. More protons, stronger pull, increases. And if it increases, therefore, what happens to the non-metallic character? Yep, Emily? It increases. So our good metals are up here in the corner. Excellent. And we can do the same argument with the ionization energy. What happens to the ionization energy as we move to the right? Yep, Jory? It increases, right? It's a stronger pull. Stronger pull increases all that stuff. Increases. And then how is our metallic character over here? How are these as metals? Jory? Decreases. They're really crappy metals. They're so crappy we call them non-metals. That's true. I'm just saying. All right? Okay, so there is a summary of all the things, right? And again, I guess it all comes down to this. As we move this way, the electrostatic force increases, right? And that's the thing that we argue, right? This has to do with the fact that we've got more protons, right? There's the whole argument. When you make study notes, you want to make things short and sweet so that when you start, memorizing it, it's easier. But when you move to the right, the electrostatic force increases. That increases the pull on other electrons. That increases the pull on its own electrons. As you move down, we've got here more orbits. And what does the electrostatic force do? Electrostatic force decreases. All right? So there is a little summary of it all, and it's all about the forces. The only thing we came across that we couldn't argue orbits or protons was the formation of the negative ions, the anions, and the more electrons you put in it causes an increase in repulsion, and that makes the anions bigger than the neutral atoms. It was the only one we couldn't use that for. Okay, so let's go back to the PowerPoint, and let's bring, that's all good. And there is the chapter review questions out of the textbook. You have the rest of that trends in the periodic table sheet, right, which essentially is the non-metal stuff that we did today. And then, like I said, practice problems.